Experiment 13 and 14 is going to be a continuation of our qualitative analysis experiments, where we're going to try to determine whether specific cations are present in an aqueous solution or not. We've already done one experiment in terms of the qualitative analysis scheme. If you take a solution that contains all possible cations that exist, and you want to be able to identify whether any one or multiples of those are present in an aqueous solution, the technique we use is to separate out small clumps of those positive ions at a time so it's easily analyzed. So the first thing we did back in experiment 5 is we took an unknown solution, and this could have contained all possible cations that are known in the universe, and we added a precipitating agent, hydrochloric acid. The reason we added hydrochloric acid is that the chloride ion will only be insoluble with silver ions, mercury 1 ions, and lead 2 ions, therefore separating those 3 cations out from all the rest of the other possible cations that exist. So in experiment 5, we took this white solid, silver chloride, mercury 1 chloride, and lead 2 chloride, and went through a procedure where we separated them and then identified them. As you may recall, when you take this white solid, if you add hot water to it, you cause the lead 2 chloride to dissolve. If you take that aqueous solution and add potassium chromate to it, then the lead ions that are present would precipitate with the chromate ions, and a yellow precipitate would indicate the presence of lead. The remaining white solid would be the silver chloride and the mercury 1 chloride. If you treat that with ammonia, the mercury undergoes an autooxidation. It gets reduced to elemental mercury, which is black, and gets oxidized to mercury 2, which forms a white precipitate. And so the presence of a black-white solid would indicate that mercury had to be present. The silver chloride actually dissolves in ammonia because it forms a complex ion, diamine silver 1. And if we take this solution and acidify it, we cause the ammonia molecules, which are bases, to turn into ammonium ions. The complex ion dissolves, and the silver ions can then bond with the chloride ions in the solution, and a precipitate is reformed, verifying the presence of silver. So that was the separation and identification of the group 1 cations, silver, mercury 1, and lead 2. We're now going to take the remainder of the cations, which are on the right side of this bracket here, all the other ions that did not precipitate in group 1, and we're going to now try to separate out a second small group. These are going to be called the group 2 cations. The precipitating agent is going to be the sulfide ion. And because sulfide comes from a weak acid, if we adjust the pH of its solution, we can vary the concentration of sulfide ions. And we can actually select only a small number of these cations to precipitate out. Because naturally, sulfides are insoluble with tin, copper, antimony, bismuth, iron, cobalt, nickel, aluminum, zinc. That's a ton of them. But if we make the solution really acidic, we're going to lower the sulfide concentration, and all of those will not precipitate out, only a smaller group will. So in today's experiment, you're going to be taking essentially this solution that's on the right side of the bracket, and you're going to be adding sulfide ions. And we're going to make sure the solution is very acidic, so we're going to add hydrochloric acid. And the sulfide ions are actually going to come from an organic molecule, thioacetamide, which in solution decomposes into hydrogen sulfide, the weak acid, and then produces the sulfide ions. Because the solution will be very acidic, we're not going to have very many sulfide ions in the solution, and under a very low concentration of sulfide, only the very insoluble sulfides will precipitate, so we can actually precipitate out only copper 2, antimony 3, and bismuth 3. And so today's experiment, 13-14, will be the separation of these 3 cations of group 2 and then their analysis. So the technique we're going to use today is going to be the procedure where we're first going to separate out the antimony from the copper and the bismuth, and then analyze that. And then we're going to separate the copper from the bismuth by first dissolving the solid in nitric acid, and then adding ammonia, in which we're going to find that copper would be present if a deep blue solution is created. And then bismuth with the ammonia would actually form a solid bismuth 3 hydroxide. And then we're going to eventually verify that by actually reducing it down to elemental bismuth. In the following experiments, we'll take the remainder of the cations that are up there at the very top right, or the most right. That's the solution after the addition of the thioacetamide, the iron, cobalt, nickel, aluminum, zinc, barium, calcium, magnesium, sodium, potassium, ammonium. And then we're going to separate out a subset of those, but that's going to be the group 3 cations. That'll be for experiments 16 and 17.